Okay, I'd like to give you guys some quick principles about the way things look in 3 dimensions. Um, a lot of people are having trouble with things like depth because we're dealing with, well, a flat screen. How do you get depth on a flat screen? Well, I'll show you the first depth cue. What you have to rely on is when you have a flat screen, you only have one image. You don't have two eyes which are giving you two separate images of the same object at slightly different angles to give you that depth perception. So supposing that when you do a drawing, you only have the one image. You've only got one image but for two eyes. So the thing is that when you cover one eye, you don't lose all your depth perception. There are still other bits of information that are available to you when you have one eye. So when you want to learn how to draw and be able to get the sense of depth on a flat picture, you have to have the sight of a one-eyed man, and you need to be able to pick up on the same things that the one-eyed person can see. And one of the first depth cues, the most obvious depth cue that the one-eyed man has to tell him what's closer, what's further, is overlap. Whenever something is overlapping, for instance, my hand in this sketchbook, obviously the object that is overlapping is in front. So that's the first depth cue. The next depth cue is something I would like to call is a spacing. So if you look at the 2 points of these things, I mean they're about the same, roughly about the same length, but there's a certain amount of spacing between the top and the bottom of these two pens. The start and the end. So whenever one object is closer than the other, you notice how the spacing is increasing when things get closer. So by a change in their spacing, and also in the overlap, you can see how they overlap, you can tell what's closer and what's further. Now, mind you, you don't have to have the separate pen to know that things are getting closer and further to you, because when things are in motion, you are able to see the change in spacing as things get closer and further. But when you have two objects, we assume instantly that they are the same size and the spacing is the same, but we can tell that as things get closer, the spacing is different. Another thing that we have to rely on is the directional spacing. So you've got the spacing at the bottom and the top of this pen, but as something turns towards you, you see how that spacing it's decreasing. In fact, the spacing reaches 0 when the 2 points converge. So that is another depth cue we have. This particular depth cue is telling us, it's telling us not so much depth, but it's telling us orientation. It's an orientation cue, and it's telling us the orientation of an object based on the distance between these 2 points. Okay. Now, another interesting thing about this whole the depth spacing between the 2 points is that if you look at this sketchbook, for instance, right, we know that the spacing between the two corners is the same at the top as it is at the bottom. But when I turn it this way, look at the difference in spacing between the far edge and the near edge. Okay, there's not all that much difference, but as this gets closer and closer, wow, actually you'll start to see that there's a huge proportional difference in the spacing. You'll find that now the bottom edge is so wide that it takes up past the bottom of the entire screen, and the top is still fitting inside. Maybe if I use something a little shorter, let's just try going from my index finger to the tip. You can see that when you get really close, okay, now one end is filling the screen while the other side is only taking up a small amount. And even if I just put my hands like this to keep the size consistent, to keep the distance consistent, it's still the same spacing, okay? But when I get really, really close, you'll start to see that there's a huge difference in the proportionate spacing between these two things. So the proportion of the spacing changes different. It's much greater when you're up close. The closer you get, the greater that proportion, that disproportion becomes. But when you're further away, see right back here, even though one is in front of the other, it's very hard to tell. So the further you get back, the harder it is for the less. It's almost like money. Distance is kind of like money. The more you have of it, the less the change matters, right? So this is only a very small change because there's so much distance. But when you're really close, like to a poor man, this small amount of distance is like it's like pennies to a poor man. Okay, this is like pennies to a rich man. So is that. All right. There's another thing I want to show you. If you imagine that there's an object sitting up here in space, okay, that there's a ray that comes from your point of view to this object. There's a sight ray, all right? Now, if this object travels along the sight ray, you notice that its position is not changing, right? The center of this point, that does not change at all, as long as this thing is traveling towards the sight ray. The only thing that's happening is the spacing between these points is increasing. Right? So as long as the object travels along the sight ray, the position of the object will not change, but the distance between its points will increase. The other thing that happens is that as it travels along the sight ray, the object does not appear to rotate in any particular shape or form. Now, if on the other hand, this object travels across the sight ray, a little funny thing's going to happen. You might not think that this object is rotating, okay? But I'm going to rotate the camera with it this time. See, now you're starting to see the front end of it. You're starting to see the front end of the marker, and as the object travels, now you see the side, and now you're seeing the back end of it. So even though this object is not rotating, it is appearing to rotate because your vantage angle, the angle at which you are viewing this object, is changing. The relative angle is changing. Now you're seeing the back end. So another very, very important thing that people tend to miss out whenever they slide objects left and right, they don't realize that as the object slides across the sight ray, your angle on it is going to change. Now, it doesn't just work sideways, it also works up and down, because you'll see that here, you're seeing something that is very much side on, but as you look up, now you start to see the underside of things. You even get to see up into my nostrils. Okay, but when you look down, same thing is occurring, that you are now seeing the top end of this pen, even though the pen is not rotating. So just because an object's not rotating doesn't mean that as its position changes, that it is not that the angle is constant. So these are a lot of things that people tend to miss. There's this kind of rotation, and then there's the kind of rotation that you get when an object slides through space, even without rotation. So let's see, what else do I have? Let's sit down here. Yes. Okay, this next bit here, I'm going to show you on the let's get on the display here. Okay. Now, I spoke earlier about overlap. Overlap being, let's just see here. Hang on, wrong. Here we are. And I just went black. Okay. Overlap is just a simple thing where one object is overlapping another. Now, if you look at just the lines, just this small area in here, you'll start to see that this line is being interrupted by this line in front. The lines that are in front interrupt lines from objects from behind. So if you wanted to, I can say take this line and then take this line, take this line. This line is furthest away because it's being interrupted by this line in front, but this line is being interrupted by the other object in front. So again, this is a principle, this is just the overlap principle, but just applied to individual lines. So now you can get the sense of objects overlapping one another. Anyway, we'll go into further detail. I'll catch you guys later.